Alright guys, we are back for the second video. So, like I said, the last video I covered kind of the basics, the clippers, and then we got into a half-wave unfiltered power supply. So it did give us a DC voltage, it gave us a ripple value, our percent ripple and all that. So remember what we had last time is the half-wave unfiltered gave us a 13.289 volt DC out. It had a 41.733 volt peak to peak ripple, and that was the percentage of that was 110%. So now what we're going to do is we're going to go through the next one, which we're going to go through a full wave unfiltered rectifier. Then we're going to go through a bridge, and then I'll put up the numbers of all three of those, and we'll kind of start building a table and a chart to look at on how these guys go. And so at the end, we'll compare all three of them, and then we'll move on to the next step and the next step. And so that's kind of the idea with the rest of these is we'll work through several of them, and then after each of these subgroups, filtered, unfiltered, pi filtered, I'll put up the chart again, and we can kind of compare, and we'll add to it, and we'll show you guys what we're looking at based on these guys. So the next one I want to cover is I want to go through the full wave unfiltered power supply. Holy crap, and I cannot write. Power supply. Okay. So this one, again, we're going to start out where we're going to use our generator as we're going to plug into the wall, go into the primary of our transformer. We're going to step that down, and then this time we're going to go into two diodes, one on either side, and then we're going to go into our load, which in this case is a 1 kilo ohm resistor. But the other thing we're going to do is we're going to throw in our center tap for the ground. If we don't, we're not going to be able to get the full wave rectification that we're looking for. What we'll end up with is just going to, it is going to be another half wave. So we have to use this center tap. Now that's going to change a little bit of our calculations as far as like primary and secondary and stuff like that, but I'll walk you through the bits and pieces. So again, we're starting off with 120 volts at 60 hertz. Now, the first thing we need to do is we need to look at what is our primary voltage, what's our secondary voltage, and what are we going to be seeing as we come through this. So here at point A, this is going to be our primary. So again, we have 120 volts. It's not giving us an indication as far as what it is. It is an AC signal though, so we have to make the assumption that the 120 volts is an RMS. So we need to take the 120 volts RMS and convert it into at least a peak value, because then that gives us options to see it on the scope, and that's honestly the easiest way to calculate and look at these guys is to deal with AC signals, deal them with their peak values. Sometimes we'll have to do, a peak value, or not necessarily peak values, but like ranges, things like that. So we would give either a peak value or a max and a min value when we're going through and solving these things. So with that, we have 120 volts RMS. We want to convert that into voltage peak. And so again, our formula to do that was voltage peak is equal to, our voltage RMS is equal to volts peak times 0.707. So we flip these guys around until we get our V peak all by itself. So V peak is equal to the VRMS divided by the 0.707. So we plug that in there. So the V peak at our primary is going to be equal to 120 divided by 0.707. That gives us 169.7 volts peak. Now we go through our transformer, and in my case I'm using a 4-to-1. Remember in yours, when you're doing the calculations, go through with the value that you've calculated for your turns ratio. You already have the voltage, what things step down to, and so just follow that ratio again. So what we end up with is, so for V secondary, and I'm going to swap this designation around a little bit, so it's V primary in voltage peak. V secondary is going to be equal to the 169.7 volts peak divided by 4, and so that gives us a total of, same as what we had last time. I'm going to go up and cheat real quick because I can't remember off the top of my head and I didn't write it down. 42.425. Okay, so this voltage that we have, this is going across the entire secondary. So from here to here, we'll just label these points B1 and B2. So this is from B1 to B2. Okay, so the whole secondary has that voltage. But since we're using the center tap, we're going to cut it in half again and only use half of this voltage. So here's kind of where one of the trade-offs come in from using a full wave rectifier versus a half wave rectifier. So in this case, the secondary voltage that we have is the total value. But our V max coming into here is going to be half of our V secondary because we're using the center tap, so it's going to take half the voltage. So we have half our secondary here, we have half our secondary here. Across the whole thing, we have everything, but we're only taking partial amounts of it. So it's going to be half of our V secondary minus a 1 voltage drop across the diode. And that will give us the maximum voltage we have coming out, and that's going to be at point C. So we have the 42.425, we divide that by 2. That's going to give us a total of 21. So yeah, 42.425 volts peak. Divide that in half. Then we're going to subtract out the 0.7 volts peak across the diode. So what we end up with is 21.217 volts peak minus the 0.7 volts peak. So our Vmax comes out to be 20.517 volts peak. So now so the reason what this is doing is when we're transforming this guy, we have a coil coming from the top of the transformer to the center tap, but the other one's coming from the bottom of the transformer up to the center tap, because that's where our ground is and our current is going to flow. And so what happens on this is we're going to get 2 waveforms coming out of these guys. So to look at this real quick, so this is the total voltage at V secondary. Okay. When we take our center tap, so that is the 42.425 volts. This is the voltage at this is voltage with the center tap. So it's going to be the half of it. So this is the 21.217. And then we go through the diode. So what's going to happen is on the positive cycle, we're going to come through, and this half is going to come up and around and go through here, and then it's going to come back, come in through the ground, and then come back the other direction. Then the other part of the wave when we come through is going to come through down here, but because if we look at it, the voltage is coming on the opposite side, so in comparison to where from B1 is, B2 is going to be inverted 180 degrees. That's one of the cool things with the transformers. Is so if we take these signals, one off the top, one off the bottom, and then with the center tap being our ground, we're going to get 2 signals coming out, and they're going to be 180 degrees out of phase, which is what we are looking for. Because what happens is, so now that we have this signal coming in, we're going to combine together at C, and if we didn't have these diodes, what it would be is it would basically cancel each other out, because we have 2 signals coming in. One looks like this. So this is the one that's coming off of B1, and the coming off of B2 is looking like this. So if we didn't have any diodes there, when we combine these together to look back at C, what we're going to get is essentially nothing. Because these guys are 180 degrees out of phase, they're going to cancel each other out. And so just like we had with the reactance values for X of L and X of C, they were 180 degrees out of phase. They would cancel each other out, and we'd be net with a 0 voltage. So basically, essentially what we did on that thing is that we would short it out. And that's kind of just a visual representation of what happens when we short it out. We now have the 2 signals that are canceling each other out. But since we put a diode in here, what it's going to do is at each of the positive cycles of the waveforms, it's going to take the diode and it's going to put them in forward bias mode. So which means it's going to drop 0.7 volts, but then when it gets reverse bias, it's going to clip off the signal. So what we have here is 2 clipping circuits. We have one treating the original waveform, Then we have the second one, which is 180 degrees out of phase of the first, which is something we learned when we were playing with the transformers the first time. So we have B1, B2, the signals going into it. When they come out of the diode, what it does, I'll kind of slide this over, so that we have these signals, these go through diode 1, this goes through diode 2, and what we end up with is we have one signal that's cut off the negative end, we have the other signal that cuts off the negative end first, then the positive side. So now, when we combine these guys together at point C, what we have is a signal that looks like this. Hump, 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 hump. So when we're talking about frequencies, remember, it's the instances of a waveform that passes per second. So in this case, we're looking at how many times does the peak pass in the same amount of time. So we knew that this was a full wave. Sorry, this was a full wave from there to there. So we went from 60 hertz to now we have a signal that we've doubled it. Now we're going at 120 hertz. This is going to be important for when we get into some of the filtered stuff. But just understand that, with a half wave rectifier, we had just the one hump and then nothing in the same amount of time. And so we still had one positive peak and then one positive peak and then wait, and one positive peak and then wait. But when we do it this way, because we've inverted the signal, we've clipped off the negative ends of our signal, now we end up with two positive peaks that happen in the same amount of time as that signal. So we've doubled our frequency. And like I said, that's going to be important when we get going for the filtered stuff. So anyway, so with that now, we have these two signals, we have these two humps, and this is why it's called a full wave rectifier versus a half wave, because now we have the full signal being, inverted and flipped and adjusted to where we can actually use it now. So now that we have these two signals, we need to calculate the same values as before. So we need our Vmax, we need our Vmin, we need our VDC, and we need our VRipple. And I'll switch back to green just because that's what I'm going to use for this section. So V minimum, we need our VDC, we need our VRipple. So as we look at this circuit, so even with our output signal that looks like this, we have a hump right here to here. We're still charging up to the Vmax, and we're still getting all the way down. Our minimum is going to be 0. So we've already calculated what this value is, and each of these signals only goes through one of the diodes one time. So we only have to account for one voltage drop. The next one we get into, when we get into the bridge rectifier, we're going to go through two diodes, and so we have to account for two diodes worth of voltage drop, so 1.4 volts. But right now, like I said, we're only going through the one diode for each iteration, and so we're getting each individual diode once, only one drop. This comes our max voltage. So our minimum voltage, again, is going down to 0 volts. That's as far down as it's going to go. It's not going to go any lower, but it's not going to get any higher. And therein lies the problem. So now, not necessarily problem, but we have to use, the different calculations. Same ones as we used before. We'll have a different set when we get into filter. So again, when we come into the circuit, we need to solve for what the values are. So our VDC, remember, since it's an unfiltered circuit, is equal to the voltage max times 0.637 to give us the average, which is what our DC value is, divided by 2. Except for, let's take a step back and look at what we have this time. Before, that was that formula that we had before was when we had the second hump here in our, basically our time period that we're looking at. It occurred twice as often, but now that we've doubled our frequency, we've doubled everything. What we have here is we have our V average for the one side, plus the V average for the second set of the waveforms, because remember, we're still going through one single cycle of our input waveform is what we're basing this off of, divided by 2, because this is the number of parts that we're looking at. Before, this value was 0 for a half wave. So we could ignore it. But now that we did this, now we have the exact same value because we split the thing in half. We're going right off the center tap. if we, had a different one, we could adjust that down there and this would affect the average. We'd put these values in here. But essentially what we have is, since these two are, the max values here are going to be the same. So you got Vmax times 0.637 plus Vmax times 0.637. We essentially have 2 Vmax times 0.637s divided by 2, because the number of instances, those are going to fall off, cancel each other out. So our DC value is going to be just the average of just these one peaks, because they're occurring with no delay in between each other, unlike the half wave where we had a half cycle where we had no voltage. So we're still using kind of the same idea, the same formula, that we're taking the average of one portion of the wave plus the average of another portion of the wave, splitting it up as best we can, divided by the number of portions that we're looking at. In this case, we have the same portion twice, divided by 2. Those 2's will cancel. So our VDC is just simply the max voltage times our 0.637 volts. And that's going to give us our DC value. Like I said, it's a little weird to do it, but just remember that this is the formula for a full wave, because of we have these two portions in the same time frame as our input signal, unlike the other one where we only had one iteration of our sine wave, and then it was flat. So like I said, that's the formula we have here. So our VDC equals this. So our Vmax times 0.637. So we take the 20.517 volts, multiply that by the 0.637, and our VDC for this one equals 13.069 volts. Okay. 13.069 volts. Okay, so now that we have that value, let's look at solving for our V ripple. Our V ripple, remember that formula, is equal to the voltage max minus the voltage min. So in this case, it's 20.517 minus 0, because again we're going back all the way down to 0. That is going to be, in peak to peak, is 20.517 volts. Now, the last part of the power supply we have is, so now that we have our AC and our DC portion, we want to find out what the ratio of this is, and this is what we call our percent ripple. So again, percent ripple is equal to the voltage ripple in peak to peak divided by 2 root 2 divided by the voltage DC. Because again, we want to find out how much is it changing because of this AC portion. So we take the voltage peak to peak, we divide it by 2, divided by the square root of 2. That'll convert from peak to peak with a 2 into peak. And then the square root of 2 converts it into RMS. We take the RMS divided by DC, we multiply that value by 100. And that gives us our answer. So our percent ripple is equal to the 20.517 volts peak to peak divided by 2 root 2, that whole quantity divided by 13.069, multiplied by 100. And when we get that, this comes out to be 55.5%. So right off the bat, just by adding in an extra diode and then tying into the center tap, we've been able to cut basically the efficiency of this guy, or cut the waste. How effective is it? By half. So instead of having 100% variation, 110% variation, we've dropped it to 55% variation, which is, it's a lot better than what it was. So now we can actually start seeing some differences. We're not going to see as big of swings. Things are getting dialed in. Things are going to start costing a little bit more money, but between these two, and all we did was add in another cheap diode to this process. So again, these are our two values that we're looking towards. And once we get through the unfilters, I'll put up the chart, and that way we can kind of start seeing the comparison between these guys. And when it comes to the time with designing them, like I said, you have your choice of which ones of these you want to use. It just matters your parameters that you're assigned, and so you can kind of mix and match. Okay, so that's really all there is to it for that one. So that one is a half wave unfiltered power supply. Or sorry, full wave unfiltered power supply. So the next one we're going to look at, this is going to be a full wave bridge rectifier unfiltered power supply. It's kind of a mouthful, but I'll show you what it is. So we have a full wave bridge rectifier power supply. So what this guy is going to look like, it's going to start off the same as all of our other power supplies. So we plug into the wall, 120 volts, 60 hertz. We come into the transformer, which is a 4-to-1. Come into our secondary, and then this is where it gets interesting. So here's where we're going to build our bridge rectifier. So what it ends up being is it ends up being 4 diodes placed in this configuration. The secondary is connected to the top and the bottom of the bridge, and the ground comes off that point right there on the left, and then on the right comes across and goes down to our load. And then that's tied to ground, which feeds back into the other side of the rectifier and then comes out. So how this works is, again, we have 120 volts RMS. We need to convert that to peak. So we have 169.7 volts peak. We come through our transformer, which is a 4-to-1, and it drops it down to a 42.433 volt peak on this guy. So now what happens is, on the positive iteration of our waveform, the power, the current basically, or voltage, one way to look at it, is it comes up through here, it comes to this point, and it sees here, oh look, I've got a reverse bias diode or a forward bias diode. I'm going to go through the forward bias diode. Then it comes to this point, and it sees another reverse bias diode. It's like, well, that's technically an open. I'm not going to go that direction. So the current is going to go this direction through the load into the ground, from the ground up into the circuit, through the other diode, and back, because it's trying to make a complete circuit. So that's the positive iteration. The negative iteration is going to come in with the negative portion of the wave. It's going to come up, oh look, there's the diode that's reverse biased. That's essentially an open. Here's the negative part of this diode. Oh, that one looks good to me. So I'm going to go through there, out to the ground. I'm going to come back up through here, come across. And again, this guy's already been used, so it's not going to travel there, and it's going to send it back to the original spot. Back to the original one. It's trying to get to the other side of the transformer to make a complete circuit. So it's going to come down through this diode and then back up this way. So we have our positive iteration, we have our negative iteration, so we have half the wave at each time. And so what this ends up doing as well is this ends up burning. So it takes your input signal that goes from this to from the 42.433 volts, and it spits out this. Not 42. So in this case, it's going to be 41.033 volts peak, because remember, each signal is going through 2 diodes, so it's going to lose 1.4 volts, 0.7 on each of the diodes it passes through, then the rest will be dropped across our load. So this is our V secondary, this is our V out. So because it's the full wave rectifier, and in this process with those 2 waves coming and going, they're going to basically be adding together on the same point. And they're going to come in and get us this higher voltage out. So before, with the previous one that we saw, the max voltage that we had on this thing was about 20 volts. We had 20.5 volts was the max we could get out with just a full wave. When we use this bridge rectifier, even though we're going through an extra diode, it creates the pathways and the option for us to get double the voltage out. So this one, we're going to have a higher voltage, but we're going to have about the same um, uh, loss as far as the ripple, the same ripple voltage, not loss, the same variations. So that's the big plus for using the full wave bridge rectifier is we get double the voltage out, at the expense of a slightly more ripple, slightly more AC signal coming out. When we want is a pure DC signal as close as we can get. So once we come out, we have this voltage coming through, but again, now we need to find our Vmax. So our Vmax, our Vminimum, our VDC, our Vripple, and the percent ripple. And again, the VDC and the percent ripple are the ones we really care about because that's what's going to be the rating for our power supply. So when we have this type of a waveform coming out, the max voltage we're going to get is the 41.033 volts peak. The minimum voltage we're going to get, again, is 0 volts. So VDC is equal to, again, we have the average for the first part of the wave, the average for the second part of the wave, divide those by 2, but in the case they're the exact same. So we end up with the voltage max times 0.637. And honestly, we could take that, multiply it by 2, divide it by 2, because that's what we're going to get. Because we're looking at this total time frame from here to here of our one input. So this is our input. This is our output. So everything's based on the clock of our input signal. Every time we push one through, we're going to get 2 positive peaks out in the same amount of time. And so then this is going to be our new average because now we have no time in between these peaks. Whereas, like I said, with a half wave, we had a whole half cycle where there was nothing. So the VDC comes out to be this value. And we get a total of 20.517. So we run that through our calculator, volts DC. So previously, like I said, we're going to get more voltage out. So the first one we had 13.069 volt DC. This one gives us 20 just by adding in an extra diode. So like I said, it comes into what can we add versus what do we lose, what do we gain, is there anything? So we end up with this voltage DC. We want to know our voltage ripple. So we take our Vmax minus the Vmin, and that's going to be equal to the 41.033 minus 0. So we have 41.033 volts peak to peak. So that's how much we're changing. Then we want to solve for the percent ripple. So we take, remember, that's the voltage in peak to peak of ripple divided by 2 root 2. And that's divided by our VDC. That whole thing times by 100 to give us the percent. So we take the 41.033, divide that by 2 root 2, and then divide that whole thing by the 20.512, multiply it by 100, and that comes out to be 70.709%. So like I said, it's still slightly more, but it's better as far as like our output voltage. We can get it up higher versus the full wave. So now what does this look like on our output? Well, real quick, if we were to look at this guy, we would have this signal, and we would have up here, well, we know what it is. It's going to be, our signal is going to be following this. It's going to go up from, we already drew that. What am I doing? We already drew this. Right here, this is what our output signal is going to look like. And so our VDC is this value that sits right there. And then that's what our waveform is going to look like, what we measure on our scope. Now, like I said, the goal is to get that ripple down to next to nothing. We want as much of that filtered out as possible to make this the most efficient one we have, so we don't have very many changes, and to create, as pure of a DC signal as possible. So anyway, so we end up with the 70.709% for our ripple. And that's what we're looking for, is to find out how much is this going to change and what values we're going to set at. So that's really how you do a full bridge wave unfiltered. So you're just kind of looking at what is my signals doing. Just know that on a full wave, you're going to have the two humps coming out with no distance in between them, no time, no delay, anything like that. And your max voltage is going to be whatever your secondary is, minus 2 voltage drops across your diodes. The other way we could bump this up a little higher is if we use germanium diodes versus silicon diodes, because those are 0.3 volts. So we could have a 0.6 volt drop that we subtract out instead of a 1.4. So if we needed that little extra, we could swap out those components and put in, different kinds, things like that. But that's really it. And then the same formulas apply for our VDC and our V ripple. It's all, it's all based on if it's a filtered or unfiltered. Now, the way you can determine if the circuit is filtered or unfiltered is it has to have some sort of a reactive component, like a capacitor or an inductor. And in this case, we're using the inductors as a transformer, so that's not taken into account, because that inductance is already basically being canceled out and utilized in the transformer part. So we don't have to worry about that. But the idea is we have a filter that we create by using a capacitor, because a capacitor builds up and stores a charge on itself that it can use later to power the signal. And so that's what the next step that we're going to be doing is we're going to be adding in capacitors to see what happens. And the idea is, what we're going to do is we're going to charge this capacitor up really fast, and then it's going to discharge through another path, our load, and it's going to take longer. And so we're going to flatten the curve. So that's, one way to think about it is with the coronavirus stuff that we've been doing. All this shelter in place, and the reason we're doing these online classes is because we were trying to flatten the curve. We were trying to, make it so to spread it out a little bit, so that way we're not, we don't get the, 100 million, 1,000, whatever people in the hospital one day. We take that 100 million, 1,000 people and we spread it out for 2 weeks, 3 weeks, or whatever. So that way we're not overloading the facilities. And that's kind of the idea with this one, is we're trying to slow down the rate at which this thing goes to zero. And hopefully, if we can get it so it doesn't go to zero. Because if that doesn't go to zero, then now we've changed where our minimum point is, and now we've bumped up our voltage. So like I said, these are all the different things we can do. And we'll put up some problems after all this is done where we're designing a filter to some specs. So instead of just working through the whole thing and seeing what it spits out, we're going to say we want to design a filter, or we want to design a power supply that gives me a certain voltage, and then we're going to work backwards. Well, what do I need? That kind of stuff. So to kind of put these things in comparison, let's look at these guys real quick all together. So I'm going to make this chart, and I'm going to come back and reference this as we get through all of these components. But now we've done our unfiltered power supplies for all of these. So we're going to have a half wave. We're going to do a full wave, and we have the bridge. Okay, so those are our three main types of power supplies that we're going to be looking at. We're going to break those up into an unfiltered, a filtered, and a pi filtered. So now that we have this, now that we have kind of the idea of what we're going to be looking at, let's kind of compare these different methods of power supplies. So with the half wave unfiltered power supply, we were able to achieve the same setup on all these guys. The only thing is we're going to add in a little different components here and there, but once we add them in, they'll be there and they're going to react the same way. So we're going to compare the same things, just taking it the next step further. So this idea was with this setup that we have right now, we were able to get a 13.289 volt DC power supply coming out with a half wave unfiltered power supply. It had 41.733 volts peak to peak of ripple, which gave us 110.032% ripple. So remember that it's 110% is changing of this guy, the 13. So it's changing that much. The full wave unfiltered power supply, we were able to get a signal of 13.069 volts DC. So we lost a little bit of output voltage, but we cut the ripple in about half. And that gave us a ratio. So we had 20.517 volts peak to peak, which was 55.5% ripple, which is amazing. So just by adding a single diode between these, between the half wave and full wave, we were able to cut the ripple in half. The bridge circuit, we added 2 more diodes to give us the same effect as the full wave bridge without using the center tap, but then it was able to take the alternate phase of the transformer, utilize that, but we're able to increase the voltage. So what we ended up with in this one was a 20.517 volt DC signal. And we also had 41.033 volts peak to peak. And that ended up giving us a ratio of 70.709%. So what that is basically saying here is, comparing between the full wave and the full wave bridge, is we gained 7.5 volts of DC voltage coming out of this thing. Our ripple went up, but in comparison, it only went up 20%. So we have a total of 70% ripple, 41 volts peak to peak, 20.53. So this is the big thing here. This is the big avenue here, is we get a higher voltage out than any of these guys. The difference between the half wave and the full wave is we're able to cut the ripple in half by doing it this way. We lost a little bit of our max voltage, but the trade-off is there. Is maybe we have a little bit less design that we can do with that, but it gives us the ability to have a tighter signal. So now the next part that I'm going to do, and I'm going to end this video here on that note, and so the next video is going to be our filtered versions of these guys. And if we have time, we'll get into the pies filtered in the same video. I kind of hope that we do, depending on the time. And then the idea here is then we'll come back and we'll finish filling out this chart with what each of these look like. So we have a half wave filtered, full wave filtered, and then the bridge full wave filtered, and then we'll get into something we call the pie filter. So it's going to basically be filtering it out twice. That one takes a little bit more work, but again, it's not too bad. We will get into it, and I'll show you guys the tips and tricks. The nice thing about these guys is the beginning stages of this is all the same. So we're using the same input, 120 volts RMS at 60 hertz. We go through the same transformer. In this case, it's the 4-to-1. We go through the same diodes using the same drops, the 0.7 volts. And then the only thing different is what's going on with our output. So the next stage, like I said, is going to be filtered. So we're going to add a capacitor in here to start changing how this is going to work. So the capacitor, as it goes, it's going to charge, and then it's going to charge almost instantly because it's coming right out of the bridge rectifier, and there's very little resistance. So its time constant is very, very short. So it's going to charge almost instantly compared to its discharge, and then it's going to discharge through the resistor on the end. Then it'll discharge through there, and then as the next wave comes form, it's going to charge up. So we're going to see this drop in its minimum voltage, or I guess increase. But what we're going to do is we're going to see the decrease in the amount total that it's changing. And one of the things there is we can manipulate is by changing the capacitor and the resistor to increase or decrease that time. How long do we need it to be charging for before it actually says, okay, I'm done, and starts charging back up. And so those are some of the knobs and levers that we can turn and adjust to get this thing to kind of sing and dance, to dial it into where we want. But anyway, there's the look at unfiltered power supplies. And again, as always, if you have any questions, please let me know. You guys have all my contact information, and I will talk to you guys on our next video.